Hello, I'm Steve Lewis. Welcome to the sixth and final module of Applied Statistics for Healthcare Data Analysis. This course is funded by a grant from the United States Department of Labor and uses a curriculum designed by Carnegie Mellon University. Today we're going to pick up the thread of inference about the parameters in a population from our sample statistics. And in particular, we're going to talk about hypothesis testing for the relationships between variables. You may recall from the last module that we mentioned two particularly important points about inference and specifically about hypothesis testing. First, the importance of correctly sampling data from our population. That we had to ensure that our sample was randomly drawn from the population so that any one case had an equal opportunity to be included as any other case. And second, that we had to state our hypotheses so that they could be appropriately tested. That our stalking horse or null hypothesis clearly states the lack of any relationship between the variables of interest. And second, that our alternative hypothesis is appropriately stated in terms of our research question. So for example, if our research question is, did a particular variable improve or increase in value, then our alternative hypothesis has to be stated in terms of an increase in value in order for us to draw appropriate conclusions from our test results. We also talked about the structure of the process of hypothesis testing, and we noted that it parallels to some degree the four-stage model of statistical analysis we've been following throughout the course. The first step is to state our null and alternative hypotheses correctly for purposes of our research questions. The second is to correctly collect data so that our sample is random and large enough to support inferential analysis. The third is to perform analysis using the correct test to develop a test statistic whose value can be determined in respect to its probability given our null hypothesis. And then fourth is to draw appropriate conclusions in terms of our research question from the probability associated with the test statistic we find by our testing. Now, before we move on, I want to make sure that we're clear about the different kinds of variables we're going to be talking about. The first is to make sure we understand the distinction between a categorical variable and a quantitative variable. A categorical variable is one where we can think in terms of proportions distributed throughout the population, and a quantitative variable is one where we would be dealing with the means of a distribution of values. The second distinction we need to make is the role of a variable, specifically as the explanatory or response variable in a relationship. And the choice of test, the choice of test statistic we want to create is driven by those two considerations. What class of variables we're dealing with, categorical versus quantitative, and what role the variables play, either explanatory or response. So probably the most common relationship you're going to be asked to look for in a research environment is with a categorical explanatory variable and a quantitative response variable. And when we are looking at that kind of relationship, two considerations come into play. The first is whether we assume that a relationship exists between the two levels of a categorical explanatory variable. For example, let's say that the particular variable we're interested in is the presence or absence of a copayment incentive in a benefit design for using hospital emergency department services, particularly for non-emergency events. There, the two samples that we would use, the no copay versus the copay populations, could be independent. They could be, for example, enrollees who are covered by or supported by one employer with a copay and a second employer without a copay. Or they could be mutually dependent. They could be the same population before and after a copay was imposed. So in both cases, if there are only two levels of the categorical explanatory variable, we would be using a t-test to develop a t-statistic, but they are two different t-tests, depending, as I say, on whether we assume that the two levels of the explanatory variable are dependent or independent of each other. Also, it makes a difference whether we are looking at a two-level or a multi-level categorical explanatory variable. If we're looking at more than two levels of the explanatory variable against a quantitative response variable, we will use what's called an analysis of variance, or ANOVA, which produces a test statistic called the F value. If we are looking at a categorical explanatory and categorical response variable, we'll use a test called chi-square, and the value is similarly called the chi-square value of the test statistic. And it doesn't matter in that particular case where both the explanatory and the response variables are categorical, how many levels of the categorical variables we can have. We can have two of each, two of one and three of the other, four of one and five of the other. Finally, if we're looking at two quantitative variables, both the explanatory and the response variable being quantitative, we will be using a form of t-test for the R value, the correlation value, between those two. In any case, whichever test statistic we use, we will want to look at the probability associated with the value of that statistic if the null hypothesis is true. And just as the case when we were testing hypotheses about a single variable, the question comes down to whether the particular statistic value we got, the result we got from our test, is so improbable if the null hypothesis is true, the hypothesis of no relationship between the two variables, that we can reject the null hypothesis. Then we would say that yes, there is a relationship. What we can say about that relationship is dependent, as we said earlier, on the accuracy of the alternative hypothesis relative to our research question. We haven't talked at all about the case where we have a quantitative explanatory variable and a categorical response variable. That is largely outside the scope of this course and involves a mathematical amount of effort that, quite frankly, I'm not even willing to get involved with. So at that point, I think we have reached the conclusion of our subject matter. I want to thank you for your time and your attention, and I really want to encourage you to embrace these tools. I know they're not immediately intuitive, but as you become more familiar with them and more comfortable using them, I think you're going to find them very, very valuable in dealing with the rapidly expanding opportunities and demands for analysis in healthcare, both at the clinical and administrative levels. You're going to be exposed to new data resources that didn't exist even a few years ago, as electronic health records become both more widespread and more interoperable, as claims and billing data sets also become more integrated, and as epidemiological data sets become both more integrated and more electronically available. You will have data resources and questions to answer using those resources that didn't exist even a short time ago and are rapidly evolving even now. So you are engaging in a very exciting new field, and I wish you all the best in doing so. Take care, and thank you again.